consulent for both of those things. But basically, I'll come and write code for you, or do talks or courses or whatever. And today, I'm going to talk about one of my favorite coding topics, which is concurrency. And I think very often, concurrency is presented as this, oh, this is super difficult. You really need to know what you're doing. Do not touch this unless you're this ninja programmer. Don't you love this? Rock star coders or ninja. You have to be this god to, even consider working on anything to do with threads. And I think this approach is problematic in several ways. I mean, firstly, that's what's fun about programming is challenges, right? And if something is really difficult, we shouldn't be like, oh God, well, let's not do that then. Yes, by all means, you need to know what you're doing if you're dealing with concurrency. But the solution should be, well, let's figure out what we're doing then, And my goal isn't to make everyone write their own, concurrency frameworks. But if you understand the fundamentals and know what problems are being solved and how it actually works beneath the hood, you will use the frameworks available to you better, because that's another problem. If you don't understand what's going on, you're more likely to misuse the tools and libraries provided for you and add these weird custom hacks to kind of work around. You start your own threads because you don't understand what the framework you're using is doing for you. So, my aim here isn't really to necessarily teach you like how to use one framework or how to use another one, but to kind of delve into the how it all works, so you'll be better able to understand the tools of your choice. And also to kind of, just think a bit about what the problems we're solving. I think so many of the problems in concurrency, we take some of our problems kind of for granted, and we forget why we have them in the first place. It's like maybe we're solving the wrong problem. So let's start from the beginning. What is concurrency? Well, concurrency is multitasking, but there are many types of multitasking. There is, some things you can genuinely do at the same time. Like I can wave my arms and talk at the same time. If I had to, stop talking every time my arms were waving, we would be here until tomorrow. So thankfully, some things can easily be totally parallel, done in parallel. Like you can attend a video conference meeting while you're sitting on the toilet. Here this is parallel execution. That's not what I'm talking about. There are some things that you still have to deal with. Shared mutable state is still a problem if you're doing parallel execution. You don't want the video conference people, you don't want them to have anything to do with what's going on down here. You need to have, you need to separate, your shared state needs to be clearly, handled well. But when it comes to performance, there's an obvious performance gain in doing things in parallel, because you are actually, performing two things, well, twice as fast because they're done at the same time. But that's not concurrency. Concurrency is, if you have kids, like trying to have any, on the phone or otherwise, trying to have any kind of adult conversation with your kids in the room at the same time. It's just like, you're like, oh yes, 10 o'clock. No, God, don't, that's not a toy. Hang on, okay, sorry, yes, what were you saying? And you're always like, you're doing multiple things, but you're not really doing them at the same time. You're going back and forth, and it's painful. And there's not necessarily any performance gain here. If you're doing things in true parallel execution, you're actually getting a performance gain. Here, this phone call is going to take probably 3 times as long because you're having to keep your kids alive and your house from blowing up at the same time. And the reason you're doing it anyway is because, there's this, demand on you to be responsive and to be, if you're not on the phone, you're missing out on whatever deal is going on there. If you're not looking after your kids, they're gonna, strangle each other or blow the house up. So, you really, there's this need for liveness and responsiveness. You don't want your UI to freeze up totally while something's going on in the background. You need to display a progress bar. So even though that progress bar is actually, destroying the performance, it's still a necessary step because, sometimes you need your system to be responsive. So, right, so that's concurrency. That's what we're talking about. So look, okay, say you've got like 3 tasks. that take like a second each or something. And if you execute them in their in sequence, you're gonna first do the one, then do the second one, then do the third one, and it's gonna take 3 seconds in total. So if you do this concurrently, each one of these will be assigned a thread. And this is on the JVM, of course, because the JVM is based on the operating system's thread model, right? So each of these tasks will get its own thread, and it's going to look like this. It's probably going to take, that's actually slightly misleading because the overhead of context switching is probably going to add some time to that. So doing it concurrently is going to take longer, but at least some of it is going, some of it's being dealt with at any, they're all kind of being done at the same time. But of course, this is for CPU-intensive tasks. That so far I've been talking about, CPU-intensive stuff. If your CPU is working on it, there's no performance gain, and there's actually performance degradation by doing things concurrently. But most of our tasks, especially now that we're doing more and more distributed operations, most of our tasks involve a significant amount of just waiting. We're calling some external service, we're calling a database or something, and we're just waiting for the data to come back. So in this case, if we've got like I/O-bound tasks, then that's when we can start seeing a performance gain from doing things concurrently. Because of course, once your thread is blocked, that's the signal to the CPU scheduler to say that, don't worry, you don't need to spend time on me, I'm blocked. Just move on to the next one. Yeah, so then you can do this in like half the time or a third the time or whatever, depending on how much time you're waiting. So, and this is the concurrency mechanism of, that our operating systems implement, and it works really well. And it's kind of ironic that the blocking mechanism, blocking a thread, which, as I'm sure you are all aware, is what everyone's saying not to do, right? We do not want to do blocking operations. When we're doing concurrency, if we want performant concurrency, you cannot block, right? But that is precisely, the blocking is precisely the mechanism that enables performance gains on concurrent operations. That's the purpose of blocking, is to actually provide a performance gain. So, but yeah, so why, but we'll get to why. But so here, for instance, at some level, this underlying concurrency model that our operating system is giving us, it works fine. Like here, I've got a loop. I'm, starting up 1,000 threads, and I'm telling them all to sleep, because that's a blocking call too, right? This works fine. This takes 1 second. This does not. There's no performance problems. This blocking model, see, we're blocking 1,000 threads, no problem at all. But if I increase this, and this is using like your default memory settings for your Java application, on my machine at least, if I just increase this to 3,000, I don't see a performance degradation. What I see, of course, is an out-of-memory error, right? What? Like in 2016, I'm out of memory from like a couple of thousand threads? This is a disaster. Like in pretty much every other domain, we've stopped solving memory issues, like a decade ago. This is so, 1998 or something that we were worrying about memory consumption. But in some kind of way, pretty much, or a very large percentage of the problems that we are dealing with when it comes to concurrency and frameworks is due to this fundamental limitation that our operating system has provided us with a concurrency mechanism that works fine, but it doesn't scale. It doesn't scale up. I mean, yeah, sure, you can tune your parameters, but you're going to get to like a couple of thousand threads, and that's all it can handle. And whereas you have, and this is, of course, where blocking is a problem. Because if you, if you can't have more than a couple of thousand threads, they're all blocked, that means that, like here, for instance, you can get around the out-of-memory thing by having like an executor service. And you can say, well, I've only got 1,000 threads, don't add more, because then I'll get an out-of-memory exception. Like here, okay, I can now do 3,000 blocking calls, and it's going to complete, but it's instead of taking 1 second, it's going to take 3. And on all of that time, my server sitting there, it's doing nothing. The entire system is just totally it's not doing anything, yet it can't do any more. And this is of course why blocking is a problem on the JVM. And interestingly, frameworks like Erlang, which were made in the 80s, and that the whole VM, the Erlang VM, was built to handle concurrency and distributed operations like that. And they do not have this problem because they don't use the operating system's thread model. They don't use the operating system's concurrency mechanism. They've made their own one. And it scales. And this is why in Erlang and in Go and languages like that, they can block fine. So they can have nice sequential blocking operations without any penalties whatsoever because they have a scalable concurrency model. Whereas on the JVM, because the whole platform is based on a concurrency framework that doesn't scale, we have to basically just work our asses off to work around. We can't use the operating system's performance mechanisms because if we block, because each thread now has to do many, many things. And if you block one thread, you've obviously blocked the whole, then nothing else gets done. So I am going to switch to some code. So let's see how IntelliJ looks on this thing here. And am I in presenter mode? Yeah, can you see that? Yeah? Okay, cool. So here's So here's my my example. So we'll just run that. That's going to take 5 seconds. So I'm just sleeping here. So again, for some reason the activity monitor isn't showing, and I'm in presenter mode. Basically, this machine is not doing anything. It is just blocked, yet it can't execute anything. If I were to submit, so I've got this thread pool of 1,000 executor with 1,000 threads available, and if I add this new task here to say hello JDD, if I run that, it's gonna take 5 seconds for that thing to run. Which is very unsatisfactory, considering that my machine isn't actually doing anything, but it's refusing to do my task. So, and one way of solving this, of course, you can start adding different executors to handle different kinds of tasks. And this is what at a very simplified level, what frameworks like Akka will do for you. You take your tasks and then each task is then run by an actor. And the actors are then run in different kind of thread pools with different settings. So you can have some actors that are more long-running tasks that run in certain environments, and then you have other ones that handle short-lived requests. And then you can kind of group your tasks so that altogether your system stays responsive. Anyway, I don't have enough time to go into the details of how it works. But basically, frameworks like Akka, they try to maximize the effect of the existing underlying threading model that we're dealing with. But what I want to focus a bit more on is a different approach that I will show you. So here I have, just for an example, so here I'm saying I want to do 10,000 now, as opposed to 5. Remember, if you're doing just normal thread pooling, trying to sleep 5,000 times will take 5 seconds if you have 1,000 in the thread pool. Here I'm trying to run 10,000. So let's try to run that. So here I have made my own method here. I'm saying sleep for 1,000 milliseconds. And then, so let's run that and see how long it takes. Yeah, so that took just over 1 second. So here I am sleeping 10,000 times, and altogether it only takes 1 second. And the way that this is done using a single-threaded event loop. And this is what frameworks like Node.js, that's what they do. So they're saying you know what? They're kind of like Erlang. You're screw your operating systems threads. That model doesn't work. we're going to make our own one. And so in a single-threaded event loop, let's go to the implementation here. I've made a, want to go there? No. Right. So here is my, just for illustration purposes here. So basically you've got, instead of using the threads, you've just got one thread, single-threaded, and you have a list. So instead of having a list of threads doing your tasks, you have like a queue. Here I've made a concurrent linked queue that takes in tasks. So here I am adding, I'm adding my sleeping task. And each task is kind of split in two. So you have your kind of input parameters to the operation that needs to be done. And then you have what needs to be done when that is completed. And for anyone doing JavaScript, you'll be very familiar with this. You've got your promises, and you've got your do this, and then this is the callback that happens afterward. And how this works under the hood is here you're saying, I'm starting a thread. I'm saying while it's not interrupted, and then I'm polling my queue. I'm saying, well, is there anything for me to do? If there is, then I check, well, is it done? If it's done, then I run the callback. If it's not done, I just put it back on the queue. And this is how, if you like asynchronous I/O operations, and this is kind of how it works in the background too. If you're making a network call, if you're doing like an HTTP request, I mean, you're still creating your socket at a lower level. I mean, it has to be there. You're doing a network call. You have to create your socket. It's still there. But instead of your thread just sitting there waiting for the results to come back, just like for this task list here, you're just polling the socket. You're saying, well, do you have any data for me? And then you check, is it complete? If it is, fine, great. Then I can go and do whatever needs to be done afterwards. If it's not complete, then I'll just check you again later. And that's all asynchronous non-blocking I/O is at a lower level. It's just you're polling the socket. And there's some extra overhead in that, because then you have to check. You have to keep hold of the data that you've got so far. Wait until it's complete, and then at the end you do it all. But this is basically how it works. But here you can immediately see the problem. Like if your callback code or anything in here blocks, your entire application grinds to a halt because there's only one thread. So this is really, really, really essential that you do not do anything here that takes a lot of time or that blocks that one thread, because that one thread is all you've got. And I've mentioned Node.js already, which uses this kind of mechanism. But there's one on the JVM too that I don't think is getting hardly, I don't know, Vertex. Have you guys heard of Vertex? Who's heard of Vertex? Yeah, some people have heard of Vertex, but I'll show it to you, because this is a single-threaded event loop mechanism that is implemented on the JVM. And you can write, Java on it. You can write JavaScript, or there's several other languages too. But it runs on the JVM. So if you want this kind of, because this is very highly performant, but many people are reluctant to having their servers run on Node.js. Like, wow, I can't have my server in JavaScript. But the Vertex framework. It runs on the JVM, and so I would feel far more comfortable with that anyway. And I've worked with this on production. Works fantastic. With some, I'll get to that here. So Vertex. So here's just an example of how you would set up. This is I've only got experience with it as a kind of a web server, web backend thing. Works. This is how you'd set up your web server. What you can run this to is really lightweight. So you start up your Vertex. This gives you, by default, it starts up one event loop per core. And you're pretty much, with regard to the shared mutable state stuff, you're guaranteed that any request that comes in, it will only ever, be handled in that one kind of event loop. So this is really good for, you don't have to worry about locking and, synchronizing your data structures, because, again, there's only that one thread. You're only on one thread. So that's another benefit of this approach, is you don't have to worry so much about, multi-threaded, code accessing the same data structures, because you only have the one thread. But yeah, so you start up, address already in use. I'm already running one. Okay. But yeah, so let's start it up again. Bam, it's up. It's really lightweight. You can set up, so here you set up your routing. Like I want to have, here you can add like parameters to your URL. This is pretty much what you'd expect from a web server. It's really easy to set it up. I want to handle this with, this method here. This takes in your routing context. Your context will have access to the response that you can write to, the requests to get parameters. But the only thing you really don't want to do is, again, you can't block. And while this approach, and like, vertex stuff, it's super performant. The documentation is fantastic. But I must say that working with this kind of non-blocking API, it is so extremely frustrating. You've all seen these like callback hell, situations that you easily get into with JavaScript, like jQuery, like and you can easily get that in a vertex environment too. Like here, for instance, I wanna get person data from a particular city, right? And then, so I request person data, and then I have to, instead of, in a sequential operation, you can just request data, and then the next line down, you can, process the result. You can't do that here, because you have to put the code to handle the result into the callback, and then, so when the response comes in, then do this. And then, of course, the next thing I want to do, I want to do another request to get even more data, and this quickly ends up being really, really, really ugly. But it doesn't have to be like this. You can write, Node.js code like this. You can write vertex code like this, but it doesn't have to be that bad. This is a lot better. So here's the same kind of example, but you can use. They have. Perhaps annoyingly, they've got their own object called future. So this is not the Java util future object, but this is a vertex-specific one. So here I'm creating, like, I'm going to have a future, result, and then I'm saying that in my result handler here, I'm assigning the result to that future object. So I'm saying here, complete this with whatever the result of this call was. And then I'm doing this here. So this kind of looks like sequential code. I'm doing one call here. I'm doing another one there. And then I'm kind of joining all the futures. So when they've all completed, then I want to, write my response or write my the result to the response so people can see the result. So with a bit of help with the frameworks, you can also, there's good support for RX Java, which is a great library for handling asynchronous future streaming results. You can get your code to look pretty nice, but it's still it's still really frustrating. Can you imagine, like, when every method here, if it's your HTTP client or your JDBC clients or your MongoDB clients, I mean, nothing has a return value. Because having a return value means blocking, right? Because you're waiting for that return value to come back. So just unit testing. You have to put your assertions inside a callback. And it's really, really, really frustrating to work with. So again, this single-threaded event loop system works. It works really well. It's super performant. But again, make sure you actually have the problem it's solving. Like, I'm from Norway. We're a tiny little country. Like, even our big sort of public service software stuff, like, we're only a couple of million inhabitants. Any service that we're providing is probably not going to be used by that many people. So, you need, because, the underlying concurrency framework that the JVM uses, just threads, like your Jetty, web server will use. I mean, it can handle, thousands of, people at the same time doing stuff. And if that's your if that's your scale of operation that you're making some kind of corporate thing for all your employees, that might be more than enough. That might be more than enough. Really make sure that you actually need to do more than a couple of thousand things at once before you start implementing something that's going to add a lot of complexity to your code. Because I guarantee you that once you start doing this, there's a lot more code involved to try to make it pretty, and lots of people are not going to put that effort in, and you'll end up with code that's very fragmented and hard to understand. You can easily end up there anyway, so make sure that it's worth it. But yes, so that was one approach. So you have like different thread pools. Akka maximizing the threading model that you already got. That's one approach. You've got the single-threaded event loop as used in Verdix that you can use. But there's also another interesting approach, which kind of tries to solve the problem that they've solved in Erlang. It's like, well, what if we could have more threads? That's the reason we're having all this trouble in the first place, is that we can't have more than a couple of thousand threads. Why do our threads suck so much? Why don't we make our own ones? And there's some guys at Quasar who have started working on this with some very interesting results. So, let's start with the sleeping implementation here. So with the Quasar framework, this is not like a library you drop in that you use, but you basically compile your code with the Quasar agent, and then you rewrite. They've got their own kind of class called a fiber, which has pretty much the same API as a thread. It's like here I've got a new fiber, and instead of taking, like a thread takes a runnable, the fiber takes a suspendable runnable. But these things have the same kind of APIs as their equivalent, threading classes. And here you have a sleep method. But what the Quasar agent code does, it looks for all of these kind of fiber blocking actions, and then it adds lots of bytecode manipulation magic, and it will then turn this into multiple subtasks that are put into fork join thread pools. But the result is that this looks like normal blocking code. So here I'm starting a fiber, and I'm telling it to sleep, and then right after I'm done. So this is like a blocking call. I wait then and then countdown. Though this is actually let me go back to explain. Are you familiar with countdown latches? Countdown latches are awesome for which example did I have that in? Sleep with callback. There. Yes, countdown latches are awesome for testing concurrent code. I was going to tell you about that here, and I forgot. So this here, a countdown latch, you give it a number of times it's going to count down. So you can do countdown, and then you can do a wait. So in this case here, for my single-threaded event loop example, I'm saying that every time I'm done sleeping, I want to count down. And then in my main thread down here, I'm saying, okay, I just want to wait until everyone's counted down. So if you want to do like assertions on, if you've got this test and you want your test is going to call production code that's going to spawn different threads, if you have countdown latches injected into the code that's running in the different thread, you can then in your test this here will return a Boolean, so you can even assert that this actually did count down completely, and then you can do your assertions afterwards. So this is a really useful tool. But let's see, back to my fiber example. But there I had to do that in the callback. But here I'm doing this. I'm doing this afterwards, just like in a normal sequential operations. I'm saying countdown when it's done. So if I run this, so I'm doing with a million. Remember in my single-threaded event loop thing? Oh no, am I not? Oh, this keeps happening. Sorry. This. No, hang on. Did it complete? Okay. So and this illustrates. So this is. I'm kind of happy this happened, because so anyway, it did a million sleeps, and it completed. It took 8 seconds, but at least it didn't actually, it does actually, somehow emulate this idea that you can have actually have a scalable, a number of threads. And they've implemented plenty of of libraries, like for all your Apache HTTP clients or whatever. You can pretty much like here, for instance. You can just very simply convert your existing code, your existing blocking code. Like here, you've got your closable HTTP client. This is a standard, Apache, interface. And by creating it with a Fiber HTTP client builder, it will have them run on their fibers instead of on threads, and you will, you'll be able to scale your solution far more than you would just using your normal threading approach. But that when I've never used this in production, so I can't go and say, use this, but you should definitely try it out. But I must admit, like when I do this, especially when I try to push the boundaries and see how much can I do, I keep getting all these weird error messages, and so I'm not convinced. I don't feel comfortable telling you guys to go out and use it, but it's a really interesting project to go look at. And there are, as I say, there are lots of, if you already have existing Java code that's blocking, and you're experiencing these issues of your application just freezing up and it can't handle the load, have a look into this, because there are plenty of things that are, there are plenty of these standard libraries that they've actually created their own implementation of. So you don't have to change your code much at all, and you might actually see the performance benefit you want, without even introducing anything else. So, yeah, have a look at Quasar fibers. And I have time. I would like as a final element here, when we were talking about this, not blocking and stuff, there's so much advice out there about this, like, oh, synchronous RPC is a crack cocaine of distributed programming, and you might think, wow, yeah, that sounds awesome, but like really, I mean, when you're calling this external service, not only do you risk your application freezing up because you're blocking up all your threads, but the argument goes also that you don't want to expose yourself to danger if that other system sucks. If it breaks down, then your own you don't want your own application to crash just because the other system is poor. And this, good advice. But there's one element here that I think is not adequately conveyed. Like if you've got your chain, the saying goes, your chain is no stronger than the weakest link, right? And that's pretty much what we're saying here. But the solution isn't to, like, no one gives a shit if this item here, if that one's super strong, it never goes down. No one gives a shit, right? If this weak thing breaks, someone has to deal with that problem. Yeah, and having like queuing in between there, like kind of decoupling everything and just putting things on a queue and letting everything be asynchronous and fine. Okay, that might solve your problem, but it might not. Sometimes especially if you are relying on getting data from that other service, if it's down, you kind of want, you need to know that it's down, and handling the exception might be better than not even knowing it's there. You don't want to end up, I don't know if you're familiar with Monty Python's The Black Knight, but basically this guy, King Arthur chops his arm off and he keeps fighting, he chops both arms and both legs off and he keeps going, right? He's like, oh, I've had worse, and you don't want your application to be like the Black Knight, If your arm's off, maybe you should stop fighting, maybe you should at least be aware of the fact that, like, okay, time out, let's just get this all sorted out and then I'll get back to you later. Just know what kind of problem you have. I was involved for a while ago. I worked for Western Chico, and we were doing real-time control software for land seismic operations, which is kind of a weird domain, but basically you're looking for oil in the desert. They put out a spread of sensors, which are basically accelerometers, so they're measuring vibration. And they had like 100,000 sensors or whatever spread out. And then you send these guys big trucks that have big metal plates that get put into the ground and they vibrate. Yeah, and that vibration goes into the rock and it goes back up again. So ironically, these are called, vibrators. And, as like the only female person on the team, I obviously get assigned to work on the vibrators. I have to say that this is where I learned about test-driven development. Anyway, the whole point is, because there was so much, talk about, we need to, we don't want, the vibrators to stop working just because some other component in the system isn't working, right? So we introduced this massive asynchronous, queuing JMS messaging system, right? With the idea that, we don't want any one compartment to go down just because some other part did. And it was a disaster. It just didn't work. Because, when these guys, they'd communicate over radio, so what would happen was these guys would say, oh, I'm ready. They'd put their pads down. They were ready to go. They sent, and I would receive this, my code was in the central servers. I'd receive the signal, and I'd be like, okay, they're ready. Give me a time to start. And if that system wasn't listening, then that message would be put on a queue, right? My saying that they were ready, would be on the queue. But of course, there are people driving these things, right? So they noticed that nothing was happening, so they'd put their pad up again, right? A new signal would go back to my component saying, oh, we're not ready, we aborted, and then I'd be like, oh, abort, and I'd put that on the queue. And then someone would be talking on the radio and like, oi, what are you doing? You shouldn't be aborting, good, get ready again. So they'd put their pads down again. Okay, new message on the queue. And then when the other component starts up again, then there's suddenly, it reads, I'm ready, I've aborted, blah, 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 blah. And the whole system would go nuts, right? It would be like powering up all the sensors, powering down all the sensors, powering up all the sensors. And it was a complete mess. When we went back to synchronous RPC, things were far more sane. Because when I got a ready message from them, and I said, we're ready, and I got an exception back, I could tell them straight away, oh, sorry, the system's down. Go, go have a cup of tea, right? So being aware of the exceptions was actually a really valuable thing for us to do. So again, just make sure that, non-blocking asynchronous, it might be the right thing to do, but, make sure that you know what problem you're solving. So, wow, I'm out of breath. Thank you.